In this video, we are going to discuss about passive circuit elements. What is a passive circuit elements? An elements which doesn't generate or produce electrical energy are called passive circuit elements. That means an elements having no source of energy is called passive circuit elements. A passive circuit elements either absorb or store energy from sources. There are three passive circuit elements: resistors, inductors, and capacitors. In the case of resistors, it absorbs energy and converts it into heat. In the case of inductors, it absorbs energy and stores that energy in a magnetic field. And finally, in the case of capacitors, it absorbs the energy from the source and stores it in an electric field. Let's see the details of resistors, inductors, and capacitors and their voltage current power relationship in this video. First of all, let's see resistors. The property of resistor is resistance. Resistance is the property of a material due to which it opposes the flow of electric current through it. That means the opposition offered by a substance to the flow of electric current is known as resistance of that material. It may be represented in this way also. Resistance is the opposition offered by the substance to the flow of free electrons. Atoms and molecules of the substance obstruct the flow of these electrons. Certain material offers very little opposition to the flow of current. Those materials are termed as conductors. Example: silver, copper, gold, aluminum, etc. Similarly, certain material offers very high resistance to the flow of electric current, and those materials are known as insulators. Examples of insulators are glass, rubber, mica, drywood, etc. The conductivity lies between conductors and insulators are known as semiconductors. Example: silicon, germanium. So resistance is the electric friction offered by substance and which causes production of heat with the flow of electric current through it. The practical unit of resistance is ohm and it is represented by this symbol. Suppose we are applying a voltage source across a wire having a resistance value R. If the voltage applied across, the potential difference applied across this wire is 1 volt. If that 1 volt produces 1 ampere through this wire, then we can say that resistance of that wire is 1 ohm. That is, a wire is said to have a resistance of 1 ohm if a potential difference of 1 volt across its ends causes 1 ampere current flow. The resistance of a conductor depends on several factors. It depends on length of the wire, area of cross section of the wire, it depends on nature of the material, and it depends on the temperature of the conductor. So the resistance value is directly proportional to length of this wire, L. Resistance is inversely proportional to area of cross section of the wire. It also depends on the nature of the material. It is represented by rho. Considering these three things, we can write down the expression for R as R is equal to rho into L by A, where rho is specific resistance or resistivity of the material. So different material is having different resistivity value, specific resistance value. From here we can write down the expression for rho as RA by L, as unit of R is ohm. This is A is having meter square, L is having meter. So the unit of specific resistivity is ohm meter. Now let's see voltage current relationship in the case of resistor. For that, let's consider a circuit like this. A voltage source V is applied across the resistor R. Here only one current I is flowing. That is the current flowing through the resistor R. IR, it is represented by IR. And as current I is or IR is flowing through this resistor, a voltage drop occurs across the resistance R. Let it be denoted by VR. In this case, VR is equal to the supply voltage V. So, VR can be expressed as IR into R, where IR is the current flowing through this resistor R. Similar way, the power loss or power dissipated in a resistor is current into voltage, that is current through the resistor and voltage across the resistor. As VR is equal to IR into R, we can write down this expression PR is equal to IR square R. We can also derive in this form also power is equal to power dissipated or absorbed in resistor R is V square by R. So this is the voltage current relations in the case of resistor. Next passive circuit elements is inductance. Inductance is the property of a coil that opposes any change in amount of current flowing through it. If the current in the coil is increasing, a self-induced EMF is set up in coil in such a direction so as to oppose the rise in current. Similarly, if the current in the coil is decreasing, a self-induced EMF is generated or set up in the coil in such a direction so as to oppose the decrease in the current. It is denoted by L and its unit is Henry and it is denoted by capital H. Similar to resistance, the inductance depends on several parameters. Inductance is directly proportional to the square of number of turns. It is directly proportional to area of cross section of the wire, and it is inversely proportional to length of the coil. And also it depends on the magnetic material and it is denoted by mu, that is permeability of the magnetic material. So considering these four facts, we can obtain the relationship in order to find out inductance from number of turns, area of cross section and length of the wire as L is equal to mu into N square A by L, where mu is absolute permeability of the magnetic material, N is number of turns of the coil, A is area of cross section of the coil, and L is mean length of the coil. Now let's see the current voltage power relations in the case of inductance. As I mentioned earlier, in the case of inductor, it opposes any change in current. This change in current is opposed by generating a voltage. That voltage is known as self-induced EMF across the coil. So that voltage is denoted by this expression, that is self-induced EMF in the case of inductor is V is equal to L into di by dt. So di by dt represents change in current with respect to time. So this is one of the important relation in the case of inductor. So from this equation number 1, we can write down the expression for di like this. Di is equal to 1 by L V dt. Now in this equation, we can integrate both sides. So integrating this equation and both sides, integral di, the current is increasing from I0 to IT, which is equal to 1 by L. Here dt is the variable, so time is increasing from 0 to t. So integral I0 to IT di is equal to 1 by L integral 0 to t v dt. Integration of di is I with limit I0 to IT, that is IT minus I0 is equal to 1 by L integral 0 to t vt, where I0 is initial value of current through the inductor. Or in other words, we can write down the expression for I of t as I of t is equal to 1 by L integral 0 to t v dt plus I0. So this equation, that is self-induced EMF in the case of inductor, that is V is equal to L into di by dt, and IT is equal to 1 by L integral 0 to t v dt plus I0 are two important relations in the case of inductor. If the initial value of current through the inductor is neglected, Current through the inductor can be expressed in this simple manner. That is, ILT is equal to 1 by L integral 0 to t V dt. Now let's derive the expression for energy stored in inductor. We know V is equal to self-induced EMF in the case of inductor as L into di by dt. Let energy supplied to the inductor from the source during the interval dt be dE. So dE is P dt. Power into times gives energy. So what is the time here? Here the time is dt. So dE is equal to P dt. What is P? P is equal to V into I. So dE is equal to V I dt. We know V is equal to L into di by dt. Substituting, dE gives L into di by dt I dt. Now we can cancel dt and dt. So the final expression becomes Li di like this. So dE is obtained as Li di. That is, energy supplied to the inductor from the source during an interval dt is Li di. Now the total energy supplied to the inductor when current is increasing from 0 to I ampere, which is equal to integration of this energy during the interval 0 to I. So E is equal to, that is, total supplied energy to the inductor is E, which is equal to integral 0 to I dE, which is equal to integral 0 to I. Instead of dE, we can write down this one, Li di. L is constant. Integration of I is I square by 2 within the limit 0 to I, which is obtained as total energy supplied to the inductor when current is increasing from 0 to I ampere is half Li square joule. Now let's see a simple problem. So this is very important. Energy stored in inductor is half Li square. Let's see this problem. An inductance of 3 millihenry has a current I is equal to 5 into 1 minus e raised to minus 5000 t, that much ampere. Here we need to find the corresponding voltage and maximum stored in energy. Here the given parameters are inductance value, that is 3 millihenry, current value as 5 into 1 minus e raised to minus 5000 t, that much ampere. Here we need to find out voltage and Emax. We know the relationship for finding out voltage as L into di by dt. We know the expression for current as 5 into 1 minus e raised to minus 5000 t, that much ampere. What is the differentiation of e raised to minus 10x? It is minus 10 e raised to minus 10x. What is the differentiation of minus e raised to minus 10x? It is, this minus is already there, into minus 10 e raised to minus 10x. So same situation is coming here also. Differentiation of minus e raised to minus 5000 t is this minus into this minus, that is represented here, minus 5000 t into minus e raised to minus 5000 t. Substituting the value of L as 3 into 10 raised to minus 3, we can obtain the value of V as 75 into e raised to minus 5000 t, that much volt. Here what is the value of maximum current? When we are substituting t value as infinity, this part becomes 0. Under that condition, we can obtain maximum current. I max is nothing but 5 ampere. Now we can easily find out Emax. What is Emax? Half Li square. Substituting these parameters L and I, we can obtain energy stored in the inductor, that is maximum energy stored in the inductor as 37.5 millijoule. Next, let's see the third passive circuit elements, capacitor. The property of a capacitor is known as capacitance. It is the property of a capacitor to store electrical charge when its plates are at different potential. And the practical unit of capacitance is farad, and it is denoted by capital F. So in the case of capacitor, there are two plates which are separated by an dielectric medium. So this is dielectric medium. So this is plate 1, this is plate 2, and which is separated by a dielectric medium. Say the distance between these plates be d. The capacitance of a capacitor depends on several parameters. It depends on the area of plates, it depends on the distance between two plates, and it depends on the medium between plates, that is dielectric medium. The capacitance of a capacitor is directly proportional to area of the plates. It is inversely proportional to the dielectric medium width, that is distance between plates, and it also depends on the medium between plates. So C is, capacitance value is directly proportional to A by D, which is equal to epsilon A divided by D, where epsilon is absolute permittivity of the medium between plates. That is the permittivity of this dielectric medium. If Q coulombs of charge is given to one plates of a capacitor, and if potential difference across these two plates is applied as V volt, then the capacitance is calculated by means of this equation. C is equal to Q divided by V. So a capacitor is said to have a capacitance of 1 farad if a charge of 1 coulomb is required to establish a potential difference of 1 volt between its plates. So that is the definition of 1 farad. Now let's see the current voltage relations in the case of capacitor. We know Q is equal to C into V. We know the expression for current as dq by dt. So instead of Q we can write down this expression. Now I is equal to d by dt of CV, that is C into dV by dt. From here we can write down the expression for dV as 1 by C I dt. Just like in the case of inductor, if you are integrating both sides of this equation, here dV integrating it with the interval V0 to Vt, 1 by C integral integrating this current over the interval 0 to t, we can obtain the expression for Vt as, that is voltage across the capacitor, as 1 by C integral 0 to t I dt plus V0, where V0 is initial voltage across the capacitor. If you are neglecting this initial voltage across the capacitor, then the expression for voltage across the capacitor is obtained as 1 by C integral 0 to t I dt. Now let's see energy stored in inductor. We know I is equal to dq by dt, that is d by dt of CV, that is C into dV by dt. Energy supplied to the capacitor over the interval dt can be expressed as dE, which is equal to power into time, that is power is Vi, time is dt. So energy supplied to the capacitor over the interval dt, that is dE, is obtained as Vi dt. Instead of I, we can use this expression C dV by dt. Now dE can be obtained as V into C dV by dt into dt. dt and dt get cancelled. dE can be obtained as V C dV. The total energy supplied to the capacitor when the potential across the capacitor is increased from 0 to V volt is, say it is represented by capital E. It is the integration of dE over the interval 0 to V if the voltage is increasing from 0 to V volt. So after solving this one, we can obtain the total energy stored in capacitor as half CV square joule.